The composition of fascia can be split up into two parts: cells and the extracellular matrix, or ECM. The cells mostly consist of fibroblasts, which these fibroblasts pretty much serve the role of maintaining the collagen network in the fascia. And besides fibroblasts, there's mast cells, immune cells, nerve cells, cells for vessels such as arteries or veins. But for the focus of fascia, I think fibroblasts are probably the more important piece to look at, especially in terms of the mechanical function of fascia in the human body. The extracellular matrix, as the word implies, is all of the parts of the fascia that are outside of the cells. So cells kind of sit in and move in this matrix of that consists of fibers, which in this case is mostly collagen fibers, although there are some elastin fibers, and then what's referred to as a ground substance. And this is kind of a fluid environment in which chemical exchanges take place within the body. I think it was kind of like exchange of like lymph fluids and things like that. Now, the collagen fibers consist of so there's many different types of collagen types that exist, but mostly we see in fascia are collagen types 1, 2, and 3. And these each have slightly different characteristics. So type 1 fibers are like those in the skin, in the tendons, and parts of the body like that. Type 2 fibers are ones that are more like in vertebral discs and sort of kind of the cushioning parts of the body. And then type 3 fibers are those that sort of make up the organs and are within the organs themselves. Type 3 fibers are also found in arteries and smooth muscle. So type 3 fibers can be considered to provide the structural scaffolding for things like arteries, organs, the periosteum, which is kind of the connective tissue that surrounds bones, and things like that. Type 1 fibers are more like the tendons, ligaments, and aponeurotic fascia. Type 2 fibers are cartilage, vertebral discs, and things like that. And type 2 is generally thinner and holds more water, so it's kind of like that cushion. Type 1 is denser and has a aligned lattice-like matrix. Now, there are a couple different mechanical loads that we see in the human body that fascia will be subjected to. The first one we'll cover is tension, which is when the tissue is pulled in a direction. In this image here, we see tension is the example used as the Achilles tendon when the calf is stretched or if the calf is contracted. Now, when tension is applied to fascia, we see an increase in type 1 collagen being secreted, and this also improves the collagen alignment, or this lattice-like structure of the fascia, and also increases its strength or stiffness. So this response to tension in the on fascia, which improves the collagen alignment, may be what people mean when they talk about fascia building or fascia activation. However, I have yet to see anyone fully explain it that way. I don't think people who use those terms know what they're talking about, know or even referring to this, or even know that this exists, because they're kind of using it out of context and without any real support from what I can see. Maybe they know, and they're trying to just use terms that are easier to understand. Maybe not, I don't know, but this is the closest thing to fascia building or activation that I could see. So next we have is compression, where the tissue is pressed on itself. The example we see here is cartilage in the knee, subjected to compression of gravity and forces of weight of the body. So under the compression, we see an increase in type 2 collagen, and this results in a secretion of proteins or proteoglycans, which have hyaluronic acid, which acts as kind of a lubricant, and glycosaminoglycans, or sometimes abbreviated as GAGs, GAGs. These are hydrophilic in nature, meaning that they attract water and hold water. And in opposition to what happens under tension, when under compression, we see a decrease in the collagen alignment as well. Now there's also shear force mechanical stress, and this is when tissues slide past each other. And you see here in the image shown below, when the ankles dorsiflex, the tissues of the extensors slides against the tissue going across. Now under shear, there's a production of lubricin, which lubricates movement as well, and this also increases. There's also an increase in fluid at the edges of the tissue, which helps lubricate movement. And now when we look at here, we see collagen types 1 and 3 are roughly equivalent, but they're both greater in number when compared to type 2 fibers. Now looking at all three of these mechanical stressors, we can look through various parts of the body and see that the fascia in specific areas will be adapted to its specific mechanical environment. So areas that are subjected to a lot of tension will have more collagen 1, type 1 fibers. Areas that are subjected to a lot of compression will have more type 2 fibers, and those in areas where there's a lot of shear will be will contain more lubricin and have a equivalent amount of type 1 and type 3 fibers to have that glide of tissues going across each other. Now, habitual movement, posture, repetitive activities, we can now see may affect or change the fascia in certain areas. So we see an example of this with a lot of desk work, cell phone use is very common, and that has resulted in neck issues, because now the neck is always being in a state of flexion, so there's more tension along the fascia going across the back of the neck, resulting in increased stiffness of that tissue. So fascia has some level of elasticity, and that is represented by the amount of elastin in the fascia. Elastin is a fiber that is able to actually stretch to 230% times its passive length. And so we see in tendons, they can stretch about 3 to 4% before damage. So they stretch a little, but not a ton. And then we also see elastic properties in both active muscle contraction and passively via mechanical load. So rather than actively contracting a muscle, if it's being stretched to a position, just like in passive stretching. And so depending on the fascial tissue where it's at, it will have varying percentages of elastin. So the elasticity of fascia and muscle is important because now in movement, it can be utilized as a sort of mechanical energy storage, like a spring. So if you think of bounding, jumping, throwing movements, if you examine them, you generally will see a counter movement prior to the actual movement. So there's the wind up before the throw. You generally see the arms swing back and a dipping down before you jump up, bounding left and right. There's the crisscross contralateral movement in bounding, and even sprinting, running. These are all elastic movements or where the elastic property of fascia comes into play. Now, there's a concept of what's called hysteresis, and that is the amount of energy during the loading and unloading that is lost. And this can be improved through training, applying loads and unloading the fascia or tendon. And this of course in the body would be through movement. And so another point besides the elastic properties of fascia is the nervous system component. So muscle spindle cells interface with the nervous system and help regulate muscle tension during movement. And these muscle spindle cells are part of the paramycium. And so since these sense tension and are part of a feedback loop to the central nervous system to regulate the muscle tension, abnormal tension in the fascia due to adhesions or something just that's suboptimal or out of the ordinary for that particular part of the body will influence the muscle spindle cells and either cause muscles to overactivate or underactivate during particular movements. So the overall idea of focusing on tension in some of these videos is that movement in the human in the human body, or just even animals as well, operates on tension. So movement comes about through changes in tension in muscles, and which are transmitted through the fascia to move your bones body around in space. So the whole idea of movement, pretty much all of movement is due to tensional changes in the body. So check out the references. It's not my area of expertise, especially the area surrounding neurology and the cellular structures and things like that. So check out the references for yourself.